I will start with chapter 11. Okay, about Fourier analysis. Okay, so first of all, I define periodic function. And so a function defined on the real line, okay, is called a periodic function. There exists a positive number p. We call this p as a period of f of x, such that f of x plus p is equal to f of x. So for a function f of x, this function may have many different periods. Okay, may have different periods. But the smallest one, the smallest period, okay, so the smallest period of a periodic function is called the function period of f of x. There are infinitely many periodic functions. So let me define the function. Okay, so f of x basically is tangent function. But as we know, tangent function cannot be defined at x equal to r multiple of power 2, right? Because we cannot define tangent function. So for those points x, we will define the value is 0. Okay? So define that. And this function is periodic. Okay? With the fundamental period I. Okay, so the smallest period of this periodic function I. So you can say that 2 times pi is a period of this periodic function. 10 times pi is another period of this periodic function. Okay, you can see there are infinite many periods for this periodic function, but there is only one fundamental period. Right? Now we observe that 1 cosine x, sin x, cosine 2 times x, sin 2 times x, cosine nx, sin nx. Okay? Or periodic function of period will be high. Right? So you can see that they are all a periodic function with period or period to pi. But the fundamental period for each of them may be different. Right? So, for example, the fundamental period for these two functions is 2 pi, of course. But the fundamental period for these two functions is pi, not 2 pi, okay? They are pi. Okay, is that clear? Okay, good. Now, my question is, what is the fundamental period? What? 0? Okay. Well, it's hard to say. That is an interesting question. The constant function has period approach to 0, so you can say the period is 0. Yes, right. But a better description is that a constant function has period which is any positive number. Okay, that would be a correct description, right? Because when we define period, we ask the period to be positive in all definitions. So constant function is a very special kind of periodic function. Okay, then now this function form the so-called trigonometric system. Okay, so we will study this spatial system, the trigonometric system, a lot. Now, so this is our observation. So now, so first trigonometric series A0 plus A1 cosine x plus B1 sin x plus A2 cosine 2x plus B2 sin 2x plus work is right. Okay, so this series is called a trigonometric series. from constants called your coefficients of the series, where B a periodic function of period to time if the series converges. Okay? So this is our observation. Okay? We can use this system, this trigonometric system, to form trigonometric series. Okay? And if this series converges, okay, then we know it is a periodic function, okay, of period time. And the fundamental period of this periodic function may be less than 2 pi. Okay? It depends on the coefficients. For example, if A0 is 0, and all AN, BN, when n greater than or equal to 2 are zeros, then you have only these two terms together, right? And if you have only these two terms together, then the fundamental period is 2 pi. But for other cases, that the fundamental period may be less than 2 pi. So the question in any periodic function f of x or period to time be expanded as trigonometric series, i.e. Okay, so we will answer this question in this section. Any questions about this question? Okay, so now to answer this question, we first derive necessary condition for the positive answer. Namely, if this is true, what do we have? Okay? Alright, so we will assume that one, to find the function converges or almost all x in the real line. Okay, so we assume that when we take second, we will also assume that of course the g of x is a periodic function, right? And we require this periodic function converges. It is well defined for almost all x in R. For those function which is such that for those x on the real line such that g of x does not converge, then we can redefine the function at those points. A remark is that a sufficient condition for 1 and 2 to be true is that A0, the x value of A0, and the sum of the x value of an and the Bn. Okay? Well, we have a method to test the infinite series, right? We mentioned before. So that we will. So if this is true, and we will see that. Check. The reason is that cosine and sine function is a maximum value plus 1, the minimum value minus 1. So the absolute value of sine and cosine will be less than or equal to 1. Okay. That is the property of sine and cosine. Okay? So if an, the x value of an and x value of Bn, right? They form an infinite series. Okay, and if this infinite series is finite, all right, then of course g of x converges everywhere. Okay, g of x converges everywhere. And of course, and the g of x has upper bound, of course, so that the integral always is the integral is. And you will see that this criteria is very useful because in practice, you usually are able to prove that this is true. Okay. So now, since we have assumed that f of x is equal to a0, for almost all x on the real line, the partial sum function is k of x defined to be a0 plus n comma a. Okay, the partial sum function will converge to f of x for almost all x in all. Okay, but the convergence may not be uniform. Okay, may not be uniform over the whole real line. Okay. So the convergence is pointwise. For each point x, for each fixed point x, sk of x will approach to f of x as k goes to infinity. Okay. Right, now, we observe the absolute value of the partial sum function, and we know that this is okay. So we know the absolute value of each partial sum function, of course, is less than or equal to g of x. Right? Because g of x here contain infinitely many terms. So the partial sum, the absolute value of the partial sum function is like one. And of course, all the partial sum functions and the g of x are integrable over 0 to 2 pi. Okay? Because every partial sum function are linear combination of sinusoidal functions, and the sinusoidal functions are continuous functions. Okay, so every partial sum function is integrable over one period from 0 to pi. Of course, we already assume it's integrable, right? We assume g of x is integrable. So this one, by assumption, okay, here we assume by assumption 2. Right? So, which which imply that f of x is integrable over 0 to pi or minus pi. I think maybe we use minus pi to pi. Okay. We use minus pi to pi. So f of x is integrable over many the reason is, let's say, by nominated convergence theorem. Just write down the reason, okay? So in the future, if you want to know the reason, we can check this theorem. Okay? But this time we can know, okay, what is this theorem. Okay? You don't need to know the detail. That's for you to check the note. Okay, so now we need a theorem for the orthogonality of the trigonometric system. Right, so the trigonometric system 1.2 is orthogonal as pi pi. We have 0 I think maybe I write this way. 1 times 1 times, okay? So 1 times cosine x, 1 times sine x, okay? And you integrate the product, and you get 0, a cosine nx, cosine nx, which is equal to 0 for all n, and the number is 1. So if you integrate the product of two cosine functions with different n and m, okay, then you get 0. V cosine function you get 0 too. And C times sine mx cosine mx dx equals 0 for all n greater than 1. So m can be equal to m, n can be equal to m. But so sine nx times cosine mx, and then you take the integral over one period from minus pi to pi, you get 0. So you have 4 formulas all equal to 0. Okay, so they are orthogonal because that you can think about the integral of the product as the inner product. So it's kind of inner product in linear algebra. Okay? So now I make a remark. And for those of you who has taken linear algebra last semester, then you will know what I'm going to say. Let V be the vector space of all square integrable functions over and E 3 is equal to so V consists of all functions defined over an interval from minus pi to pi, such that the square of f(x) is finite integral. So we call square integrable. So we can square it and integrate. And so V consists of all such functions, square integrable functions. And it can be shown that this set V is a vector space. Okay, it's a vector space. Okay, so I say that. Define Fg okay. Maybe I will say real value function. Okay. So now we define the bracket f in G like this one. Okay. Then is an inner inner product. Okay. Then this is become to an inner product. Okay. V. So it becomes to an inner product. That is A. The inverse product of F with itself is greater than equal to 0. And the inner product is 0 if and only F of X equal to 0 for almost all X in R. So essentially, the function as inner product with itself to be 0, then essentially it is 0. Inner product is symmetric because we are talking about real inner product. C. Inner product is linear. Okay, it's linear. So if we have a linear combination of two functions f1 and f2, and we take this linear combination, inner product with g, then it is equal to the similar linear combination for the inner product of f1 and g and f2 and g. Okay. So ABC, Alright, so note that two functions from F and G and Q are regarded equivalent if f of x equal to 0 for almost all x in R. I'm sorry. We are talking about function defined over the interval from minus pi to pi. I'm sorry. So please correct it. So in this function, in this vector space, two functions are regarded equivalent. So they are equivalent functions. Or if they are equal for almost all points in this interval. So they are identical. Essentially, we regard them as the same vector. Okay, so it means that we got f and g are the same vectors. Okay, so we got them as the same vector. Alright, so do you have any question about the setting of these vector spaces? I think that the part A is quite easy because if f is equal to g, so you have f squared, right? F squared is non-negative. So the integral of a non-negative function will be non-negative, right? So it will be non-negative. The second thing is if this integral is 0, then almost all for almost all the points, the function value should be 0. Otherwise, the integral will be not 0. Okay? So A part is very convincing, right? For the second part, you can change the role, right, of f and g. So it's symmetric, of course. The third part is from the linearity of integral. So when you put into here, by the linearity of integral, you prove C. So ABC on EC, right? You can derive ABC. Okay. So you can say that what is this? This is one, the constant function and the cosine. So this is the inner product. So the inner product of 1 and cosine x, and this is the inner product of 1 and the sine nx. 0. Okay, so and we say two vectors are orthogonal if their inner product is 0, right? In linear algebra. So that's why we say the trigonometric system is orthogonal because the inner product are 0. And for here, this is the cosine nx, cosine mx equal to 0. So if n is not equal to m, then these two functions are orthogonal to each other. Sine nx, sine mx, also 0. Okay? And sine nx, cosine mx, also 0. For these two, n cannot be equal to m, because if n is equal to m, then the inner product is not equal to 0, because they are the same function. Okay, so let's take a short break.